Welcome to classes on inorganic chemistry. It is higher secondary. It is class for higher secondary second year, and it is the continuation of class number 20. And I discussed a part of D and F block elements, and today I am discussing the second part of D and F block elements, and it is of about E naught electrode potential and stability of the ions in solution, and regarding reducing oxidizing properties of a transition element, their ascending and descending orders. So before starting electrode reduction potential, let me first define what is electrode. It is the substance or the systems or the arrangement. It is the species or things on which the oxidation and reduction reactions take place. With the help of this, we will define electrode potential and standard reduction potential, etc. So first of all, what is electrode potential? Say, in a very simple way, if you take a copper as electrode, and if we submerge this copper in copper sulfate solution, if the metal is this, with this metal, if you take a salt, electrolytic salt of same type of metal, that is copper sulfate, so that copper sulfate, there will be ion in the solution. So what's happened in the ion? From the electrode, there are two types of reaction occurs. One, this metal has a tendency to lose electron, and on the other hand, from the solution, there is a tendency of this cation to approach the metal and gain electron. So two type of reactions are taking part. So one is a loss of electron, gain of electrons. So first of all, let me define what is oxidation. So in short, loss of electron is called, and gain of electron is called reduction. It is known to you, and it is very important thing you should know. Loss of electron is called oxidation and gain of electron is reduction. So during the process in a system where there is both type of reaction occurs, one electron is losing and in other type there is a gaining of electron. So due to this fact, there is a potential difference develops between the electrode and electrolytic salt solution, and this difference is called electrode potential. Now what is electrode potential? It is the potential difference developed between the electrode and the salt solution or electrolytic solution, that is electrode potential. Now what is standard electrode potential? Now if this changes takes place in standard condition, what is standard condition? 298 Kelvin, and pressure is 1 bar, and your salt solution is 1 molar. If this is done in this condition, then it is called standard electrode potential, and it is very essential. It is denoted by E naught. Am I right? Now what is reduction potential? Reduction potential the so the extent or likelihood of a metal or a substance tends to be reduced or will be reduced is called reduction potential. Extent or likelihood of a substance tends to be reduced is called reduction potential. Now important factor I am telling, reducing agent. Very important factor you should know, minutely follow. Reducing agent, the substance which loses electron get oxidized. Loss of electron, earlier I have written loss of electron is called oxidation. So on losing electron, it oxidized, and the substance which loses electron is called reducing agent. The substance which lose electron is called reducing agent, and the opposite is oxidizing agent. Am I right? So one point you keep it in your mind, what is reducing, and reverse of this one will be oxidizing agent. So reducing agent is the substance which loses electrons get oxidized is called reducing agent. Am I right? The substance which loses electron get oxidized is called reducing agent. Now in the electrode potential concept, if you see here, these are the potentials. The substance from fluorine to lithium, last we see that one thing, this is electrode potential, that when we measure the electrode potential of a substance, we always compare it with hydrogen. It is relative. So electrode hydrogen potential is always taken as 0, and above this all are positive and below this all are negative. So with respect of the ability of a substance to accept electron or to release electron, it is measured. Am I right? So above substance, the elements are the substance which very easily accepts electron. Fluorine is substance which highly accepts electron. It gives fluoride. Am I right? So above one, those who are positive, they have the ability of the tendency to accept electron, and by due degrees, if you go downward, you will find their accepting capacity is decreasing, and at the last time, the accepting capacity of electron decreases, but on the other hand, the removing capacity or releasing or losing capacity of the substance increases. One is increasing at the top, the accepting of electron capacity is increased, and at the last, the bottom of this one, the releasing capacity, means losing electron or removing of capacity of electron, increases. So that is oxidized and that is reduced. Accepting of electron is called oxidation, and releasing of electron is called reduction. So as you move downward of this scale, you move in this way, you will find fluorine is the highly oxidizing agent, means it accept electrons, and by due degrees you will find lithium has the high tendency to release electron, to get Li positive. It will never accept electron, to lose electron. So losing capacity is called releasing capacity is called reducing property. So reducing oxidation top, and if you go downward, you will find releasing capacity is increasing. So lithium is highly reducing what substances, and fluorine is the highly oxidizing agent. So for instance, you will find the maximum of this one has got oxidizing, has got plus property, and reducing has got a negative property. So whenever you are giving E naught of something is positive value, E of something is negative value, so that from that you are asked to find out which substance is oxidizing and which substance is reducing. When you find E naught is negative, then you will tell it is reducing. When you find the value of E naught is positive, you will tell that it is oxidizing. And sometimes you will given two value of E naught, Am I right? So one is something, other is something. You always give the greater value of negative greater value is highly reducing, and negative smaller value is comparatively less reducing. And if two positive values are given, so you compare this positive value, bigger value is strong oxidizing and bigger positive value is strong weaker. A bigger value of positive value, if two values are positive, is strong oxidizing, and smaller of that positive value, if the both are positive, then smaller of this positive value is called weaker oxidizing agent. So out of this we can find out oxidizing and reducing property. So in terms of ion in the solution, that ion directly come with solution of this solution part of the stability of solution in ions, sorry, ion metallic ion or transition ions in the solution, their stability we will explain. So one of the main important thing is that the more in the substance ion is soluble in the solution, that depends of the more is the negative value, but mind that they have variable oxidation state. That concept is only valid in case of variable oxidation state. If the metal has more the negative value, they will be more stable. Only it is valid in case of variable oxidation state of the metal having various variable oxidation state. Now let us take one example, simple example. Uh, so if you are asked the electrode potential M0 to M positive for copper is positive, that is it is pure. Mind that if oxidation potential and reduction potential, if the reduction potential is positive 3.5 value, then oxidation potential of that one will be negative 1. One is reverse of another. Reduction positive, if reduction is positive value, then oxidation of the same one will be negative value. So the copper is positive. You are asked in the exam, very often asked, why the E0 for M to positive to M for copper is positive in this, and that value is 0.34. Mind that for first transition series, that is scandium, titanium, vanadium up to zinc, you will find all of the metal have negative value. If you please go through the book, you will find each and every one has got negative value, but only one exception is that copper has got +3 value. And you are asked in the exam or in entrance exam, why it has got positive value. The answer is very simple. First of all, I am showing you in a tricky way. Just you see, no need to write a lot of things. Just you strike the point, you will get the answer. Size of copper is small, hence is enthalpy of atomization is more. And one thing you mind that if energy of enthalpy of atomization is balanced by hydration energy, in the last class I told you, it should be balanced for stability. If it is not, if enthalpy of atomization is more than hydration energy, then it is positive. If enthalpy of atomization is less than hydration energy, it is negative. So here size of copper is small, enthalpy of atomization is more, but hydration enthalpy is less than enthalpy of atomization. Hence the energy required to transform copper solid to copper 2 positive in aqueous is not balanced. I told you that hydration enthalpy must be balanced by enthalpy of atomization. Here in this case of copper, we have seen that here hydration enthalpy is less, means enthalpy of atomization is more due to its smaller size and lone pair of electron, unpaired electron. Am I right? Unpaired electron. Hence, it's, and on the other hand, it hydration energy loss. is less. So the energy required to transform copper to copper 2 positive is not balanced by hydration energy, hence it is positive. Now next question, just you see, copper 2 positive is reducing. Mind that reducing is means the substance which lose electron get oxidized is called reducing one. Am I right? The substance, the chromium is reducing, Mn3 plus is oxidizing towards D4 configuration. Why? So you see, now let us explain. Chromium is reducing and Mn3 positive is oxidizing towards D4 configuration. Now what is the electronic configuration of chromium 2 plus? It is D4 configuration. And what is the configuration of Mn3 plus? Mn3 plus is 3D4. So we are talking that chromium is reducing, easily reducing, and Mn3 positive is oxidizing towards D4 configuration. Very simple. If you want to make it reducing, so you should lose one electron more. So if you lose one electron, so that one becomes Cr3 plus. Am I right? And one electron, loss of one electron, here it is D3. Now if it is oxidizing, we need gain of electron. So if you add 3d5 and if you add up one electron, you are getting Mn2. Now you see here both C2 and Mn3 plus has 3d4 and 3d4 configuration. Am I right? So when you lose one electron, you are getting chromium D3 configuration, and when you gain, that is it is reducing, and when you gain one electron here, you are getting 3d5 configuration. So this is reducing because here D3 configuration, it is a very important thing whether it is stable or not. Answer: D3 configuration in aqueous solution for chromium is stable. Why? Because D3 configuration is T2G3. Because when it is in water, it makes a complex. Chromium makes a complex with water like this. It is a bit tough. You need not to explain each and everything. Just for explanation sidewise, I am showing you that chromium this. So in presence of water, so what's happened? There is crystal field splitting due to the approach of this ligand, water ligand. So the 5 orbital 1 2 3 4 5 energy level 1 2 3 4 5 energy level breaks in this way. So it is octahedral complex. Am I right? So 3 above 1 T2G and Eg. So yeah, 3 electron will occupy the lower energy level, hence it is stable. So you need not to explain in the exam, you will just show this one and tell when chromium 2 positive loses one electron, its configuration becomes D3, and D3 in aqueous solution is stable due to T2G configuration, lower energy level, occupation of electron is lower energy level, and Mn3 positive is oxidizing towards D4 configuration, because when you accept this electron, one electron is the Mn2 positive, Mn2 configuration 3d5, it is all are completely half filled, hence it is stable. So it will accept one electron to be oxidized, and it will reduce one electron to be balanced, to be stabilized in aqueous solution. Now next one, cobalt 2 plus is you are asked to explain why cobalt 27 is easily oxidized in presence of strong ligand. So let us assume a strong ligand. In coordination chemistry, you have already got carbon cyanide. sorry, cyanide, Cn negative is a strong ligand. So cobalt 2 positive is easily oxidized in presence of strong ligand. If there is a ligand, strong ligand like this, it is easily oxidized. Cobalt 2 positive. What electronic configuration of cobalt 2 positive? It is D7. I think you draw it, you will find it is D7. Am I right? So D7, you write in this, you draw 1, 7. It is normal D7 configuration arrangement in d orbital. Now, what's happened in presence of strong ligand? Strong ligand, what's happened? Pairing start. It is in what's happened? This is the configuration of D7. So, in presence of strong ligand, unpaired electron will paired up. So, you are getting this. So, one electron is left. So, this is easily removed out to be oxidized. So, loss of electron means oxidation is easily in cobalt 2 positive if there is a strong ligand, as this arrangement get paired up to give you single pair electron and it is easily removed. Hence, cobalt 2 positive is easily oxidized in presence of strong ligand. Next one is manganese 2 is more stable than ferrous 2, Fe2 positive towards +3 oxidation state. Let us see what plus is nothing but D5 and what is Fe2 plus. Fe2 plus is equal to, I think it is D6. You draw the configuration, you will find this one. You write in this way, Mn2 plus is equal to this and Fe2 plus is equal to D4. Now what's happened? Mn2 plus is more stable than Fe2 plus. So if you draw the D block configuration, you will find D is completely half filled and here D6 is equal to 1, 2, 3, 4, 5 and 1 is 6. Unpaired electron is there. It is neither completely half filled nor completely filled. So stability of this is more than this. Hence, Mn2 plus is more stable than Fe2 plus in +3 oxidation state. Sorry, I am sorry. If you want to make it +3, so what will you need? You have to remove one electron. So that is Mn3 plus. So one electron will be less, you will get this. So Fe3 in +3 oxidation. +3 oxidation means you should release one electron. So you are getting D5. Am I right? So here in this case, you are getting in this case, on releasing one electron, you are getting a stable electron configuration. But if you want to remove one electron further from D5, it is already in stable state. It is very tough. Hence, it is stable. Mn2 positive is already stable. To release one electron makes it unstable. But it is unstable configuration. To release one electron, to make it Fe3, it gives a stable configuration. Am I right? So it is unstable. Fe2 state is unstable, but Mn2 state is stable. You are given manganese, chromium, vanadium, iron, and you are asked which of these among these is more stable in solution. Answer: smaller the size of cation, higher is the stability, higher is the stabilization energy, higher is the hydration energy, higher is the stability. Because that day in my first class I told you, if the ion is small, it has high polarizability power, more the polarizability, more is the attachment of the water molecule, more is the hydration energy, more is the hydration energy, stable is the ion. So smaller the ion, higher is the stability of this ion in the solution. So you have to find out the size of the ion, am I right? So that is actually 23 atomic number, 24, 25, 26. So what we see here is chromium, vanadium, chromium, manganese, iron, right? So for time being, you assume all the plus charge are plus 3 plus 3 plus 3. It is also plus 3 for time being, you assume it. So as we move from left to right in the periodic table, we are moving left to right in the periodic table, the size decreases, its size decreases, am I right? So here we are concerned with this one, here iron 2 plus, here this manganese, here atomic number is 25, here atomic number is 26, here 3 less, electron is 3 less, means 25 and electron is 22, am I right? And here 2 less, electron is 24. So 25 proton is attracting 22 and 26 proton is attracting 24. Naturally, here the electron difference is how much? 3. Here difference is 2. So 25 is attracting 22 and 26 is attracting 24. Naturally, this attraction is more. So what's happened here? Due to this fact, here iron will come over here and manganese will be there. Other thing will remain same. So out of this, you will find the manganese has got the smallest size. So manganese is stable in the solution. The question was E0 Mn3 to Mn2. So you start from this to this always. So this is manganese, D5 means manganese 2 plus means D5, and if you want to one more electron loss, if you want to lose one more electron, you are getting this configuration. Now from here it is 3D configuration, and if you want to lose one electron, the is becoming this. So you see here you are trying to convert D5 to D4. Since it is completely half filled orbital, so it is too much stable. So to lose electron from one will take more energy, hence it is more positive. Whereas it is unstable configuration, to release one electron to get the more stable configuration is very easy, so less energy. That's why it is more positive than this. Same type of questions here. We see E0 of Mn3 positive to Mn2 positive is more positive than E0 chromium 3 positive to chromium 2 positive. Again you convert from part to this part, you see it is D5 configuration and you need to lose one electrons to get D4 configuration, and from here it is the configuration is D4 configuration is D4, and if you want to convert it D3 means loss one electron, plus 2 plus 3 means you have to lose one electron. So to lose one electron you need D3. So you see once again it is a stable configuration, completely half filled configuration. To remove one electron is very hard, so it needs more energy, hence it is more positive. But to remove one electron from one to get the stable configuration of D3, because in chromium D3 in aqueous solution is stable a bit earlier, I have told you, it is very easy. So it is more electropositive than this one. So you are asked to arrange this in increasing stability towards +2 oxidation state. All are +2 oxidation state. Now see, you are given the data E0 for chromium 3 plus 2 chromium 2 plus is minus this, and chromium element T2 equal to plus 1.5, and Fe3 plus to Fe2 plus is 0.5. So here the stability depends upon more the positive value, more is the stable. So Mn 3 to Mn uh, 2 is the highest value, so that will be the highly stable one. Number 2, which one is the least? The least value is least stable. This is the least. So chromium 2 is least stable, and next one will be middle. Last one will be middle. So highest the positive value, highest is the stability in the equation, aqueous solution, and the least the value, least is the stability, and middle is the in middle position. Now we are reducing agent out of this one. So chromium 3, the electronic configuration of chromium 3 is equal to D3, and it is D6. Now what is reducing agent? Loss of electron. The substance which lose electron get oxidized is called reducing agent. So it should lose electron. So if you want to lose this electron, 1 electron, so you are getting and if you want to lose electron, you are getting this configuration. So what's happened? It is a very stable configuration. Again and again you have got in chromium 3 in aqueous solution is very stable due to T2G3 T2G configuration. T2G3 configuration in the lower energy level, the 3 electron has occupied in the crystal field splitting part. That's why it is very stable. To remove 1 electron from it is extremely tough. But here Fe2 has configuration D6. So to remove 1 electron give you a stable electron configuration. So it will very easily lose electron. Hence Fe2 is strong reducing agent than Cr3 positive. So again you are given manganese 2 plus is more stable than iron 2 plus for plus 3 oxidation state. What is Mn2 plus? Mn2 plus is equal to 3d5 configuration. Fe2 is equal to d6. Am I right? So you are asked to get the oxidation state 3. So to make it oxidation state 3, you have to lose 1 electron. To lose 1 electron, so that you are getting configuration is 2, and lose 1 electron means Mn 3 plus. Am I right? So here you see Mn is stable than Fe2. So if you want to lose, because you need to make oxidation state 3. To make the oxidation state 3, you have to lose 1 electron. Am I right? Getting oxidation state this. So we are concerned with this oxidation state. To get this oxidation state, we have to remove 1 electron for D5 configuration. But D5 configuration is already stable. But here you see from Fe3 to get 3 oxidation state for Fe, we need 1 electron to be lost from Fe2 positive. So if we are getting Fe3, so after losing this electron we are getting this. But it is, this stage is already stable. So to remove 1 electron to make plus 3 oxidation is tough. So Mn2 is stable than Fe2 for 3 states. It is unstable because it easily loses 1 electron to get D5. After losing out 1 electron, it is getting stable. But before losing out to get Mn3, it is already stable. So you are asked to explain the trend of oxidation state in 3D series. So 3D series starts from scandium and ends in G. So outermost unpaired electron starts from 3D1. 1 2 3 4 5. After this it goes on decreasing, because 1 2 in D block 1 2 3 4 5. If it is 6, then say 1 5. Now if furthermore electron increases, atomic number increases, now what's happened? Pairing starts and unpaired electron get reduced. So what will you tell? As we move from left to right in the third 3D series, from scandium to zinc, the electronic unpaired electron goes on increasing 1 to 3 to 5 up to manganese, and then start decreasing and becoming lesser and lesser. So since oxidation state in a series depends upon the unpaired electron, number of unpaired electron. Since number of unpaired increases up to manganese, so oxidation state increases up to that level, and start decreasing up to zinc as number of unpaired electron decreases due to pairing occurs. That's why you will find iron, cobalt, copper, nickel that has a zero oxidation state. Copper, pentacarbonyl, or nickel, tetracarbonyl, all has iron and copper has zero oxidation state. Given the question is O2 and F2 stabilizes higher oxidation state of transition metal, but ability of oxygen exceeds that of the fluorine, because oxygen fluorine both has the tendency, it is valence is 2, its valence is 1, monovalent 1. So both divalent and monovalent O2 and F2 has the ability to stabilize the higher oxidation state of metal in the transition series. It is correct, but you are asked that transition metal with higher oxidation state can be stabilized by oxygen in a more extent that fluorine. This is because oxygen has the ability to produce multiple bond. Oxygen has the ability to produce multiple bond, whereas fluorine has the ability to produce single bond. Due to the multiplicity in the possibility of multiplicity in bonding in oxygen, oxygen has the higher ability to stabilize higher oxidation state of metal. That's why one example you can cite manganese. So you see, when manganese it has higher oxidation state metal, am I right? Higher oxidation state +2 to +7, it has a lots of oxidation state. Higher oxidation state of metal is has a compound with fluorine that is monoatomic, and that fluorine has, we got compound MnF4 +4 oxidation. Above that we can't find any such compound that MnF6, MnF7 like this. But you see, when oxygen is attached to that higher oxidation state of manganese, then we have seen the manganese oxygen 7 has come here to stabilize this. So that's why it is told that oxygen has the higher ability to exceed that of fluorine in the stability of the higher oxidation state of the metal. This is all about of today's class. Hope you have minutely followed the class. In my next class, with a very short time, I am coming to explain with a block element. In one class, I will complete a block element. Thanks a lot for watching the class.